Okay, so I'm going to talk to you about a project I did with the North Carolina Department of Transportation. Sort of done, sort of ongoing. There's two projects. We finished one, and the second one's ongoing. So some of this sounds like it's already been done. It has, and some of it continues, and it does. Our purpose here, the idea was NCDOT runs, they have roughly 16,000 assets, and about half of those are motorized. Okay, so they've run about 8,000 assets for which they have to do PMs on, consisting of oil changes and other things, right? And so the vast majority of those are what we would consider on-road, off-road. I mean, forget about the water pumps and that kind of stuff, right? But the on-road and the off-road, the big assets, they're getting their oil changed on a regular schedule. 5,000 miles, 200 hours, or once a year, whether it's needed or not, right? And so the purpose of this project was to look at that and see if there was a way to do a little bit better, to see if there wasn't an opportunity to extend some of those oil drains just to see if there was an opportunity. That was really the goal, is should we change our schedule? Can we make it longer? And so we set this up to understand what's going on with the oil as it ages, right? So really it's understanding how fast it's aging. It also understand in what ways it's aging. So we're trying to learn about the oil for the purposes of extending oil drains. The objective was to push the interval, not change the oil until we absolutely had to, with the overall objective of not endangering the engine, okay? So this is very quick because this is probably knowledge that all of you have. When you put oil in an engine and you run it, three things happen, right? Three things can happen. And for some reason, number two should be number one. Chemical change will occur, okay? That is, the oil will oxidize, the base oil will oxidize as the engine runs, okay? That's going to happen. You're not going to stop that. You can slow it down, you can do some things, but it's going to happen. There's going to be an oxidation process, and then the additives that are in the oil are there sacrificially, and they are designed to change. And they will either go away through a mass transfer process. They'll react with other chemicals in the oil and change from what they were into something else, so that additive's no longer what it was. Or some of them are designed to come out of the oil and form, through decomposition, and form a protective coating on bits and pieces of the engine. So the additives are designed to come out. So there will be a chemical change. That's number one. You can have a physical change. Physical change is where essentially your viscosity changes. Viscosity can go up or down depending upon what's causing it. And then as that happens, you will have corresponding changes to your density of your fluid. So that can happen, and then you can have contamination through any number of things, whether it be the water, the glycol, the fuel, your wear metals. It could be from your soot, it could be from dirt, it could be from silicon out of your seals, any number of things. But you can have contamination of your oil, okay? Chemical change will occur, physical and contamination may. What's really important is none of this is independent of the other, okay? If you get fuel into your oil, it can increase your oxidation, speed of oxidation. It will also decrease your viscosity. It will decrease your unit or your density, your unit weight. I mean, it's all interreactive, right? If you get soot in there, it blows the viscosity up. It can also change your additives in there. So it's all interrelated. So given that was sort of our backdrop of what's going to happen and what we think, how it's all related together, the method we set out was to do benchtop analysis. Right, so we're going to regularly test the oil, and we looked at sending it off to labs. And the downside of that was, if we're going to be pushing this oil to sort of its limits, we don't want to have to wait a week, 10 days, 2 weeks to get the results back, right? So we want to be able to pull the truck in, analyze the oil, and if we need to change the oil, it's still in the shop today, and we can do that. So North Carolina bought, so far they've bought 2 of these benchtop analyzers. These things are a little bit bigger than this podium. They're about this size, a little bit wider, not nearly as tall, but sit up on top of a desk, right? The first one we bought was the OSA 4 truck check. since then, and so we bought that. This is the Spectra Scientific. So yeah, that's what you were supposed to be seeing. So that thing, about the size of the podium, first one cost 50 grand. Spectra bought it. They claimed they did all kinds of fantastic upgrades. They certainly upgraded the price. As near as I can tell, it's the same machine. It's a touchscreen computer with a whole bunch of stuff behind it. Okay, and it's a fantastic machine. I'm not a commercial for or against this thing. It does chemical analysis, so it can give us all of our TBNs, our oxidations, all that stuff. It's got dual temperature viscometers in it, so we can pull a viscometer at 100 and 40 C. And then it also has an optical emission spectrometer to do the metals analysis. Basically, it zaps the oil with about literally 50,000 volts, turns it into a plasma ball, shoots infrared through it, and tells you what's in there. So a pretty cool machine, and it does this pretty quickly. We can run about 3 samples an hour through this thing. They'll tell you it's faster. I'll tell you that we've run literally over 1,000 samples, and we get about 3 an hour. Once you run an oil sample through there, you have to flush the system. So there are some consumables there. You got to buy that flush fluid. You got to flush it out every time you run a sample, and the dirtier the sample, the longer you flush. So it takes some time, but we can get about 3 an hour. Which means we can get the results in about 20 minutes, right? Which is pretty good if you really need to know what it looks like, okay? We did set some thresholds so that we didn't do too much, any damage is what our goal was. There's a whole bunch of these in the report. As Judith said, if you can't sleep at night, this will do it, I tell you. But there's a whole bunch of parameters in there. The most important one was our total base number. We picked 4. We can talk about that. Viscosity that's the SAE standard for 40 weight oil, and then we looked particularly for silicon and aluminum because those in combination tell us you've got dirt, which is a problem. Silicon in and of itself and aluminum in and of itself is not that big a deal, but in the right combination it indicates the presence of dirt, which is a serious problem. We had an iron threshold because these machines produce a lot of iron. And then potassium and sodium we were watching because in combination it's indicative of glycol. So those were sort of the important things we were looking for. So we had 3 different types of oil. The first thing we did was we tested the fresh oil. So we wanted to know what we were starting with. One of the things in North Carolina is they're required to purchase their oil from what's called Corrections Enterprises. Corrections Enterprises is the prison system, right? Those guys buy it in massive bulk and then they drum it out, and DOT buys it and sends it to the shops. So we wanted to make sure the quality of the oil we were getting to start with, okay? So we started running samples of these 3 different oils, and what we found was for a couple of them, the one on the left, I don't know if this is going to work, yeah. So this is a conventional oil. We had a conventional mineral oil. We tested it for total base number and we tested it for viscosity, and that all looked good. In the middle here you see that we have a synthetic blend. And we tested it for total base number and we tested it for viscosity. And what we saw was our total base number was a fair bit lower than where it's supposed to be per the manufacturer's specs. So they say it's supposed to be a 10. We were getting an average, and I don't remember, that's something like 15 or 18 samples averaged together. About 1.5 points less than that. All right, and you guys know about TBN, it only goes down. So we were starting down a little further than what the manufacturer said we were. And then the last one is this big group of stuff over here, the Shell Rotella full synthetic. And I had some real questions about it. We started running samples and we saw that the total base number was a little bit lower than usual. It's supposed to be at about 10.5 and we're getting about 9.5. That really wasn't my concern. My concern was this viscosity number. And so we were pulling these straight out of the bulk tank at the division shop. And we were getting numbers that were very, very close to the minimum SAE standard for 40 weight oil. And that's an average of a large number of samples because we pulled lots of samples to keep testing it. And something like 40% of our numbers were coming in under the standard. Thought that was a little concerning, so I sent a grad student out with a couple of $20 bills, and lo and behold, he came back with a couple of gallon jugs from Tractor Supply or other places, right, Napa. And we tested those, and all the results look pretty similar. So we don't think it's necessarily a problem with the oil that they're getting from Corrections Enterprises as much as it's just a little bit different than what Shell says they're actually providing you. We did the baseline stuff, and then we started testing the machines. And like I told you, there's 2 studies. One is done and one is ongoing. So on the left-hand side in the Charlotte area, we picked out 4 classes. We had 2 on-road trucks and then 2 classes of mowing tractors, okay? We pulled in a whole bunch of machines. We had 47 machines, and we were pulling samples every 50 hours or every about 1,500 miles, and we were covered up in oil samples. We ran a lot of oil samples. And one of the, and so for each of those 4 classes, we picked a small subset of machines and we put them on an extended drain interval where we didn't change the oil, in theory, until we told them to, okay? Included in that group is our IMAP trucks, and IMAP in North Carolina is the Incident Management and Patrol, and Incident Management Accident Patrol or something. It's the trucks that patrol the interstates when there's problems, right? And so in Charlotte, they run a pretty good sized fleet of those. And so we put all of those on the extended oil drain plant at one point. Right now, we're working in the Wilmington area, which is down towards the coast. We've been much more selective. We've got a small number of machines. We're running all those on an extended plan and really trying to focus in on getting the data we need. We have run, looks like 1,070 samples. When we pull a sample, we pull 3. Okay, so all the numbers I'm going to show you today are averages of 3. We don't just pull 1 because sometimes you get a weird number in the results. And so we pulled 3 and we ran them. And so you can see that in all of our different types of equipment, we got the crew cab chassis, which is just that. It's an International crew cab chassis. It's got that DT 466 engine in it. And we carried that through into a set of machines down in Wilmington that are running that same engine so that we could get sort of longitudinal data on that. We had the IMAP trucks and then the mowing tractors. And then right now we're testing some single axle dumps, those are Max, some backhoe loaders that are JCBs, and a couple of different excavators. But we're starting to get our data here. Here's what it looks like. So I know that's way too small to read in the back, but you can see the dots. This is our mowing tractors on the left, okay, and this is total base number, which I told you goes down. It's the measure of your basic reserve in your oil, ability to neutralize acids that form, okay? And so this is both sets of mowing tractors. These were John Deere New Holland tractors, probably 75 and a little over 80 horsepower, something like that. The one set, the orange data is from side boom mowers. So they're a little bit larger, they have the side boom on them. And what you see there is total base number. We tested that out to about 500 hours. We had a little problem keeping the guys from changing the oil in these tractors, even though we said don't. When you pay DOT people to change oil at 200 hours, they change oil at 200 hours, regardless of what we couldn't hardly get them to not do it. But we got some decent data. We got a decent curve, straight line curve to it. We feel that that looks pretty good. We could start to see a decrease, and if we were to project that out, we would be well over 1,300 hours before we needed to change the oil on a mowing tractor, which is probably a little long. It's certainly outside of our data range, but it's certainly not necessary to change it at 200 hours. Right? We're nowhere close to this threshold value here at 200 hours. On the right-hand side, you see those DT 466 engines. They're in those international trucks. It's a big engine and a relatively good-sized truck. That oil really didn't change. We ran that thing out to almost 13,000 hours, and that oil didn't change. I mean, there's essentially no difference in any of that. Statistically, there is no difference. Now, I will say you do see this one strange line here. We'll come back and I'll tell you about that in a second. That is one of those trucks, and that is just like the others, except the data is not like the others. We're not seeing any significant changes in that. From a viscosity perspective, so we really came down, we tested all kinds of stuff, and I'll talk to you about the wear metals and the contamination and all that. But you know, it really came down to, is the chemistry good and is the viscosity good? And so we looked at the chemistry, the viscosity. From the viscosity perspective, these are our two SAE thresholds, right? Maximum of 16.3, minimum of 12.5. So you want to be between those two. All of our mowing tractors look good, right? No problems with no real problems with chemistry, no real problems with viscosity. Those international engines, we see some of these have some fairly low viscosity. That could be some fuel dilution, we don't know. That one weird set of data is this same guy right here. I have no idea what happened, and the point of leaving that in there is that you can try to trend stuff, but when you get a weird set of something going on, I mean, I can tell you we changed the oil in that truck, ran it out to I don't know how long, through a cycle, changed it, and that's the oil that got in it. We changed it again, and it went right back into this other. I mean, it's just one oil change of one truck in the middle of 3 that we looked at. You really got to watch. I have no idea what caused that. This is where it kind of got interesting. So you saw that really slight decline, and really no decline for the international trucks, really slight decline for the tractors. These are the IMAP trucks, and the IMAP trucks are F250s, F350s. I think they were actually all F350s at this point. And we have 2 different sizes of engine. On the left-hand side, you see a 6.4 liter. So those are a little bit older Fords, had the 6.4 liter engine. On the right-hand side is the newer stuff, the 6.7 liters. Okay. Now these actually look very, very similar. And in fact, you can plot these on top of each other, and from a TBN perspective, you see that they're both dropping right at 0.000, so about 0.4 every 1,000 miles. The slope of the lines are essentially the same. And you see that we can get out there, I don't know, this bothers me. This looks like it drops a little faster, that you're probably going to hit that closer to the 8,000 time frame. These guys, we consistently ran out to 12 to 15,000 miles before we hit our threshold. Here's where it gets interesting. From a viscosity perspective, the stuff in the 6.4 liter trucks was bad. Lots of fuel dilution in there. Almost none of our data points are even inside the thresholds. The 6.7 liters, now remember, all of our fresh oil was starting right here at this threshold, some below and some was clustered right around that, but it stayed there. Sorry, the 6.4 liter had a lot of fuel in it. The 6.7 was good. Thank you. Now, we did, and I should say, these were all running that T6 synthetic oil, okay? So the question came up of, can we run conventional oil in it? Right, because we run a lot of these run a lot of miles, they get a lot of oil changes. They're the only machines in the fleet that run synthetic oil. And so they're paying a premium for this. And so we were able to pull out a couple of trucks, 6.7 liter trucks, the good trucks, figuring the 6.4s are going to quickly work their way out of the system, right? So we pulled a couple of the newer trucks, the 6.7s, and we ran a little bit of conventional oil in it. And we tried to do more, but it goes back to the DOT worker who says that truck gets synthetic. When he changed the oil, he put synthetic back in it, even though we didn't want to. But we ran a couple of oil changes, a couple of cycles through here on a couple of different trucks. And what you see is the synthetic and the conventional perform right on top of each other. And so the real question came up of why are we paying the 30-40% premium for the synthetic? Just a little bit about what's coming out of our project right now. This is very fresh. This just came out this week. This is looking at a set of tandem axle dump trucks. These are Mack trucks. And what you see here, I know it's really tough to see, but up here you see us plotting the data, 3 different trucks based on mileage, right? Measured mile odometer. And you see a fair bit of spread in the data. So we also are getting 2 other bits of data. This data down here is measuring the age of the oil in terms of gallons of fuel burned by the engine. So instead of miles, looking at fuel burn. And you see that data, exact same data, but it gets clustered quite a bit better. And then the third piece is actually measuring it by engine hours. At engine hours, it really, really tightens up, because what you see here is this one truck that's really not performing well. The oil quality is dropping significantly, the miles are not accumulating, and he looks very different than his friends. Plot him over here on engine hours, and he lines right up with everybody else. We did not have engine hours on the first project. And so this is quite from my perspective, a very interesting development. So we're going to be looking at engine hours going forward. Contamination, there was none. There really was none. So what you see here is 3 different types of contamination: water, soot, glycol. There was none. Okay, on all of our machines, this is typical of what we saw. We saw we had one machine, the turbo blew up in it, and it threw aluminum all through everything. We picked that up pretty quick. But there was no contamination other than the fuel contamination that we saw in the system. And in terms of wear metals, a lot of charts that look like this. The gist here is that all the blue dots are well below the red lines, right? Nowhere near, with the exception of some copper. We can talk about copper. With the exception of some copper, no issues at all with wear metals. Iron stayed well where we needed it. Aluminum was good. We looked at chromium. There's all kinds of stuff. This thing runs a test of about 15 wear metals. Now the copper did bounce around a bit. Copper is not really a problem. It's a soft metal. It kind of comes and goes, and that's what we would see is we would see it run up here. Now this is a bunch of different machines, but we would see it run up here, and then the next time it would be down here. It disappeared, right? And so where's the copper going? The filter's not pulling it out. We know that, right? So did some looking into that and talking to some folks, and it's copper passivation. Are you guys familiar with that? Copper passivation is where the copper will deposit itself onto the oil coolant system, and it kind of works its way into an equilibrium. And so the copper it'll form a deposit on the bits of the oil coolant system. And then what happens is when you disturb that, so when you change the oil, the chemistry changes of that system, and that copper will come off into solution, and we pick it up. And then as you run it and it goes back into equilibrium, it'll redeposit itself. And so the copper will come and go as we do that. And that's what we saw. I think I took the chart out of here. I had one in here, but it would show it, the copper would go up and then it would come back down, and then we would change the oil and it'd pop up and it'd go back down, we'd change the oil. But it's a soft metal, it's really not a big deal. So from an analysis perspective, what we found was TBN was our key. We didn't see any other stuff changing as a result of age, right? There was no relationship between the viscosity stuff and age. There was no relationship between the wear metals and contaminations and any of that. The only thing that changed with age was TBN. And we had a pretty consistent change in most of our stuff. We did see a viscosity problem, but that was specific to that one engine, and it was a fuel dilution problem. Contamination was not a problem at all. And I tell you, so unless we had some problem inside of an engine, we really didn't have a wear metal problem. And so this is kind of where it got interesting. So we looked at all the data. I'd done this over a couple of year period. And we said, okay, what are the recommendations? In that Navstar engine, that international truck, I said you could probably go to 10,000 miles and not worry about it. So double your oil change interval. You could probably go longer than that, but I didn't have any data to really support that kind of a conclusion. But felt I could safely go to 10,000 miles. In the 6.4s, keep changing it every 5,000 miles. The oil's probably okay, but you've got a fuel dilution problem in there, and you need to get that out of the system. So the 6.4s, I said leave them at 5. The 6.7s, I said you could go to 10 very comfortably. I think you could probably go a little further than that. That 4 cutoff that we set for the TBN is a very conservative number. You often see folks using a 2 or a 3 or even a 1 as sort of the bottom end of that, and we set it at 4. So I think 10,000 is pretty conservative. Get closer to 15, I'm not sure you could get all the way there. And then in the mowing tractors, you could easily go to 500 hours. I think there's opportunity to go longer than that. The data just wasn't there. We needed to run these a little bit longer. I took all of that and I said, okay, what's the value of that? So I looked at the NCDOT fleet, and only for the engines that we tested. Okay, so for example, take the Class 0209, they'll have several hundred, or at least a few hundred, of the trucks in that class. And I said, how many of those have that engine in them? So some of the older stuff will have a different engine, different make, different model, right? But looking only inside that class at that engine, there were 164 of those in the fleet of that type of truck, right? Looking at the 0311s, the larger mowing tractors, those were the 3 engines that we had. Looking only at those, how many tractors do they have that have that engine, okay? So I found the machines that matched, not the ones we tested, but all of them in the fleet that matched the specs that we had. And I looked at what their average use is. So on average, they run those Class 0209 trucks 10,000, a little over 10,000 miles a year, okay? So at 5,000 mile oil change, that would be 2 a year. If I said go to 10, you can save 1, right? So one of those, one oil change, the value of that oil change was $250. One oil change saved at $250 for those trucks amounted to $41,000 and a little over 1,200 gallons of oil. For all the 4 classes, remember that's only 4 classes that we looked at. The total, I don't know if you guys can see that down there at the bottom, the total estimated annual savings for these engines and these classes is $120,000, just by extending the oil drain interval on these. And it saves about 2,622 gallons a year in oil. So I think there's real opportunity, extend the drain intervals. I don't know how many folks have really looked into that. There's very little data out there. But I think there's a real opportunity from a savings, economic savings as well as environmental savings to do this.
I'm an engineer and a bit of a car nerd and oil guy, so I've looked into a lot of this. I had the fortune of having a several-hour conversation with an engineer in industry, an oil engineer in the industry, and his comments on fuel dilution 100% matched yours. If you've got fuel in the oil, there's nothing you can do but dump the oil. One of my questions is based on, you presented us 3 oils that the Department of Corrections, I believe it was, for North Carolina, presented. Are they locked into those 3 oils? And the reason I ask that is through my own research in the industry, I've found that, every manufacturer, whether it be, Chevron or Royal Purple, has about 4 different classifications of oil. And you touched on additive packages. I know, for example, if you buy the cheapest Royal Purple at $5 a quart, or the $20 a quart Royal Purple, your additive package change is huge. And so I was curious, obviously on your 6.4 liters, it wouldn't help to buy the best oil in the world, but on your 6.7s or your DT466s, perhaps if they were allowed through corrections to step up to a slightly different oil, it'd be interesting to see how much further you could extend that interval. So is that available to North Carolina? Are they able to change vendors for oil?
That's a good question. I don't know the answer to the part of, is it available to them? I can tell you that, well, they're running 3 different oils. I don't know what packages are available from that Corrections Enterprises system. They're running a blend down in Wilmington, and everything down there runs the blend. I can't remember it's a Fleet Supreme or something like that. No, that was the Conoco. I'd have to look at the name again, but they have different options. It's worth looking at. I mean, the limited data I have says that we ran the conventional Conoco oil inside the trucks that were running the synthetic, and it laid right on top. So to me, but that's full disclosure, that is an extremely limited amount of data. It's worth looking at. It's something we're trying to look at in Wilmington, sort of the value of the synthetic, and do we really see a difference in performance? Unfortunately, right now the machines aren't getting used enough to really give us enough data to throw that out. You're spot on. The additive package changes dramatically. I don't think I have enough data to really address that very well, but you're spot on with your comments.
Did you guys try the conventional and the 6.4 liter?
No. They sort of wrote the 6.4s off.
All right, thank you.
They had sort of written the 6.4s off long before I figured out why.
So with the extended intervals, is there a warranty concern with manufacturers?
Is there a warranty concern? Absolutely. And if you read the full research report, if you could get to the end without going to sleep, you would see that in the recommendations, that's one of the things I address is look straight up, you have to, any decision that's made using this data or any other has to be made in full consideration of the warranty issues, because there are some serious, you got to be careful. Now, that being said, I think you'll find that most of the recommended OEM oil change intervals are not terribly different from what I've recommended. I think 5,000, I don't think any of them are recommending 5,000 miles. They're probably closer to 15, to be honest with you. And so, yeah, it's a real consideration, but I think there's opportunity to do it. At least in North Carolina, there was opportunity to do it and still be in compliance.
Yeah, at the beginning of your presentation, you talked a lot about the machine and that it checked for all of the metals, et cetera. And at the conclusion of your presentation, you pretty much dialed in on everything being set pretty much on the TBN number. Is there a lower grade machine available that just checks the TBN? And if so, would you recommend it for other DOTs?
So the question, I don't know if you guys could hear all that. The question is, it all boiled down to TBN, so do you really need the $80,000 machine? You can buy a machine that just does the TBN. It's still going to be expensive. I don't know the price of it, but there is one, I'm pretty sure. I would say, yeah, go ahead, get this one. And in fact, you can upgrade from that one to the $110,000 machine that'll actually do particle counts as well. And I say, yeah, get the full set of data, because what you will see, you're not just getting the TBN, right? If something happens, right? So the way I look at it is, it really boils down to, if you're going to measure the quality of the oil, you're looking at TBN and viscosity, right? Everything else, and to some degree the contamination. But in reality, the fact that there's fuel in there is really a function of a problem in another system, right? And if you end up with a whole bunch of a wear metal or something in your oil, that's a symptom of another problem. And you need to see that and know that. So in many ways, a lot of this stuff, we call it oil quality, but it's really engine health. And I think you want to see that. And so I would say it's probably worth the money to get the bigger package.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.